I'm Professor Rad, and this is Precalc video 232, Applications of Exponential and Logarithmic Functions, Radioactive Decay. So in this video, we're going to be talking about decay of various substances. So let's just jump right into it. So our model for radioactive decay is N of T is equal to N naught e to the KT, where N of T, this is function notation, so it doesn't mean N times T, it means N of T, is the remaining portion of the substance that you started with after time T, so how much of it is left. N naught is how much you had at the very beginning. K is your rate of decay, and T is time. Now, because we are decaying here, we want to have a decreasing function. So that means we want this exponent to be a negative value so that we end up with a decreasing function instead of an increasing function. Oh, excuse me, goodness. So what that means is this K value, our rate of decay, is going to be a negative number. Okay, so if K is positive, that means you have growth. And if K is negative, that means you're going to have decay or, a population dying off, for example. Also, when we use radioactive decay, it'll often be given to us in terms of a half-life. So a half-life is the time at which half of the original amount remains. So in particular, N of the half-life is equal to half of the initial amount. So let's go through an example of applying these concepts. So we have the half-life of carbon-14 is 5,600 years. So what that means is after 5,600 years, half of the original sample of carbon is going to remain. If 2% of the original amount of carbon-14 is left in a specimen, how old is it? And we want to round to the nearest year. And I forgot my parentheses there, so pardon me. So sorry. All better now. So let's summarize what we've been told. So we have the half-life of carbon-14 is 5,600 years. So what that means is that N of 5,600 is going to equal 1/2 of our initial value. So when they tell us a half-life, they're telling us a time at which we have just half of what we started with. Now they want us to know if 2% of the original amount of carbon-14 is left, how old is it? So we want to know, what is T if N of T, the amount that we have, is 2% of the original amount, is 0.02 times our original amount. And that's it. That's what we have been given for this problem. So we haven't been given a lot, and the information that we have been given is not just a simple like T equals this, K equals this, let's move on with our lives. We've been given really kind of cryptic information. So the way that we're going to use this information is we're going to use the half-life in order to figure out the decay rate. So we're going to use this equation and this relationship in order to figure out the value for K. Once we have K, then we can form a formula and be able to solve this equation here, or figure out for what value of T will we have 2/100 of the original amount. And in all of this, it's not important for us to know that original amount. We'll see that we can get rid, it won't become important in the equation. So let's start out by finding K. So I'm going to start out with this relationship here. N of 5,600 is equal to half of my original value. Now, N of 5,600 means that I'm plugging in 5,600 for T into this formula. So I could rewrite this left-hand side as N naught, so N naught times E to the 5,600 T. And that's going to equal, K, 5,600 K, always do that, is equal to 1/2 N naught. So T is 5,600, but we don't know K, we don't know the decay rate. Now, notice that we have n naught on either side of this equation. So we can divide by n naught because we're assuming we started with more than 0 of carbon 14 here. So we're going to divide both sides by n naught, and that will give us e to the 5,600k is equal to 1/2. This is a logarithmic equation that we can solve. Let's solve it by writing this in logarithmic form. So we have log base e of 1/2 equals 5,600k. So the natural log of 1/2 is 5,600k. So to get that decay rate, we're just going to divide by 5,600. So we have the natural log of 1/2 over 5,600 is equal to k. So this is going to be our decay rate. Now, you might be wondering, you might say, Professor Ad, but you told us this was going to be a negative number. So the natural log of 1/2 is actually a negative. So let's go ahead and calculate this and get a decimal approximation. So if I have the natural log of 1/2 or 0.5, and we divide that by 5,600, we get a rate of negative 0.000123776, approximately. So in this instance, because this isn't our final ending point, I don't want to round this value now. I want to keep the precise value in my calculations. So I'm going to write this over on the side with my summary here. So k is the natural log of 1/2 over 5,600. So I have that to use that as a reference when we go to find the time at which we have 2/100ths of our original sample. So I'm going to erase this portion just so I have space to continue solving. And now we need to solve for t. So first we get k, and once we have k, we can use this relationship to help us find t. So we have n of t is 0.02 n naught. And we're essentially going to do the same thing again. So we're going to go back over to here, and we're going to replace n of t with n naught e to the kt. And I'm going to replace k with this beautiful expression. So we have n naught e to this expression times t. So I like to put the t out front so I don't think it's inside this logarithm. So I'll have the natural log of 1/2, natural log of 0.5 over 5,600 is equal to 0.02 n naught. All right, so take a moment and solve this equation for t, and you're going to round your answer to the nearest year. And after you've solved that equation, unpause the video, and I should have my solution on the board, and we'll talk through it. All righty, so I got at the end 31,606 years about. So the way I got there, so we had this equation, this is where we left off, and I divided both sides by n naught. So that got rid of that variable. So the only variable that remained was t. So I rewrote this equation in terms of the natural log. So I said log base e of 0.02 is this mess. So the natural log of 0.02 is the mess. And then what I did was I multiplied by the reciprocal of this fraction here. So that's how I ended up with 5,600 in the top and the natural log of 1/2 in the denominator, because I multiplied by the reciprocal. And then I just threw this into my calculator to get my approximate value. There we go. That's how I figured out how old the sample was. All right, and so that's going to be it for this radioactive decay. But before we leave off, I do want to check out one more thing. Poof. So we've been talking about 3 different types of applications for exponential functions, and I wanted to take a minute and just look at these formulas that we had. So when we had continuously compounded interest, we had A of t was P times e to the RT. For population growth, we have P of t is P naught times e to the KT. And for radioactive decay, we have N of t is N naught times e to the KT. In all 3 of these formulas, Notice that these are all the same formula. There's no difference among them other than the variables that are used because of the context of the disciplines where they tend to be used. So for example, A of t stands for future amount. So this is the future amount of money. P of t stands for your population at time t. How big will your population be in the future time, whatever, just like how big will your population of money be? How big will your population of creatures be? Or how big or small will your population of a substance be? Okay. So N of t represents the amount of the substance you'll have at time t. Also, all of these involve an initial value. P is the amount of money you initially borrow or the amount of money that you initially invest. P naught is the population that you have initially. N naught is the amount of the substance that you have initially. And all of these involve that rate of growth or decay. So for money, that R is our interest rate, typically given to us in percentage form, but you can write that in your decimal form for your formula. So you have your rate of growth for your interest, your rate of growth for your population, your rate of decay for your radioactive decay. So all of these formulas are the same formula. They are Y equals some initial value. So I'm just going to say P naught, just because it sounds like peanut, I don't know, some initial value times E to the RT, E to some rate times time. So if you have trouble memorizing formulas, it's better to think of these as the same concept. They're all the same concept of uninhibited growth. So I tend to remember this formula because it looks like a word PERT, whereas these are, not as easy to remember. So I remember PERT, and so if I forget my population growth or radioactive decay variables, it doesn't really matter what the symbol is, right? As long as I know what it represents and how to apply it in that new situation. So I just wanted to point that out to you because when that clicked in my head as a student, I was like, oh, this is wonderful. I don't have to memorize 3 things. I just really have to memorize 1. So there we go. So that's going to be it for this video on radioactive decay. And in fact, that's going to be it for our second unit. So yeah, in the next half of the course, we're going to be switching gears and primarily studying trigonometry. So things are going to get a little bit different pretty soon. So I hope this video helped you out with radioactive decay, applying exponential functions and solving them using equations, using logarithms. And yeah, so I'm looking forward to trig in the next video, and I'll see you then. In the meantime, have a fantastic day. Bye for now.